All right, we're going to finish our study of analytic geometry with the ellipse. And the ellipse is a set of points such that the sum of its distances from two fixed points is constant. And those two fixed points are called the foci, the plural of focus. So there are two foci for an ellipse. Now, it's really kind of simple to see how we could even construct an ellipse physically. Imagine that you have two like thumbtacks, put them in a board, and attach a string, one end of the string, to each thumbtack, and give it some slack, so it's sort of hanging loose. Then you pull it till it's tight, and if you sort of trace it around, keeping the string tight all the way around, it'll trace out an ellipse. That's basically what an ellipse is, right? So it's not that either D1 or D2 here in this figure is fixed, but their sum is always the same. D1 plus D2 is always fixed. Now, we're going to start with ellipses that have their center at the origin, and then we'll move out to a center located elsewhere. But if the center is at the origin, then an ellipse will have an equation that looks like this: x squared over a squared plus y squared over b squared equals 1. Now, this ellipse that we're looking at is sort of oriented horizontally. That's sort of the long axis, so we call this the major axis. And then here, this is the minor axis. So this equation, where it's x squared over a squared, is actually the equation of an ellipse that has a center at the origin whose major axis is the x-axis, so it's oriented horizontally. And as we'll see, a squared is always bigger than b squared, so we can kind of tell its orientation based on just examining those denominators. So this says such an ellipse has vertices at negative a0 and a0. So let's plot those points. Let's mark those down. Negative a0 and a0. These are two vertices. So an ellipse has two vertices. These points at the end of the minor, they don't have a special name. They're just called end of the minor axis. So there's 0b and 0 negative b. And the foci are located at C0 and negative C0. So here we go. A, B, and C, in this scenario, in this ellipse, they are actual coordinates. Now, in any ellipse, even if it's located elsewhere, even if the vertex is not at the origin, A, B, and C will always refer to the distance from the center out to a vertex, out to the end of the minor axis, or out to a focus. And that'll be important to realize as we work through some problems. Now, this is the standard form for an ellipse that looks like the one over here on the right. We're not going to derive that equation, but what we will do is derive an important relationship between A, B, and C. So we know that what makes an ellipse is that, or what makes something a point on the ellipse, is that the sum of the distances, D1 plus D2, is constant. So we're going to find the sum of the distances for a couple of cleverly chosen points, and we're first going to focus on this point here. That's the point A0, so that vertex on the right side. So we're going to find D1 plus D2 for the point A0. So the distance from C0, right? So it's the D1 and D2, these are distances to each of the foci. So the distance to C0, which is this distance right here, that's a horizontal distance. Right x minus left x is A minus C. And the distance from the point negative C0 to A0, in this case That's just the longer distance, still horizontal though. That distance is a minus a negative c or a plus c. So now the sum of the distances, if I add these together, is 2a. So that's d1 plus d2. Okay. So let's make an observation here. What makes something a point on the ellipse is that the sum of the distances never changes. The sum of the distances is constant. So this means that the sum of the distances, d1 plus d2, is equal to 2a no matter what point we pick. Alright, let's do this again. Let's go through this process. Let's find d1 plus d2 for the point, and I'll pick the end of the minor axis up here, the point 0b. Okay, so the distance from C0, let's go back up here and take a look at the figure. So what we're doing is trying to figure out what is the distance from this point at the top down to this focus. And what we're going to do is just use the fact that we kind of have this built-in right triangle here. And the vertical leg, that has length b, the horizontal leg at the bottom, that has length c. And so using Pythagoras, that distance is the square root of b squared plus c squared. And the distance to the other focus, going back up here, we've really already done the work because the ellipse is symmetric. So that distance is going to be the same as the one we just found. That is also the square root of b squared plus c squared. So now if we add these together, we get 2 times the square root of b squared plus c squared for d1 plus d2. But look, we've already figured out, right, the sum of the distances doesn't change. And so here we have d1 plus d2 is 2a, and at the same time d1 plus d2 is 2 times the square root of b squared plus c squared. And if the sum of the distances doesn't change, that means that 2a has to be equal to 2 times the square root of b squared plus c squared. Dividing by 2 gives us a is the square root of b squared plus c squared. And if we square both sides, we get a squared equals b squared plus c squared. It kind of looks like somebody wrote out Pythagoras wrong, because we're used to c squared being on the other side. But if you look at what a, b, and c represent here as distances out from the center to these various points, a is obviously the biggest, right? That's out to the vertex. So this equation is true. When our ellipse is centered at the origin, a, b, and c represent actual coordinates. But this is true for all ellipses as long as we interpret a, b, and c to be distances from the center. So So A is the distance from the center to vertex. B is distance from the center to end of the minor axis. And C is distance from the center to focus. And this is a fact that comes in handy, maybe not for every ellipse problem, but often enough that I keep it front of mind when I'm working on ellipses. Alright, so the standard form of an ellipse that has its center at the origin and its major axis is the x-axis, is the one we were looking at up here, x squared over a squared plus y squared over b squared equals 1. If the major axis is the y-axis, then the equation is y squared over a squared plus x squared over b squared equals 1. You probably notice they're virtually identical. The only distinction is that is the location of a squared and b squared. So if the major axis is the y-axis, then a squared appears under the y squared. If the major axis is the x-axis, then the a squared appears under the x squared. So if the major axis is the y-axis, then the vertices are on the y-axis, the ends of the minor are on the x-axis, and the foci are on the y-axis. The relationship between a, b, and c holds. A squared is equal to b squared plus c squared. And so if we're looking at the equation of an ellipse that's in standard form, we can tell which way it's oriented just by looking to see which variable is over the bigger denominator. So in example 122, we want to sketch the curve x squared over 25 plus y squared over 9 equals 1. And it begins by asking, what is the major axis? Which is the major axis? And look, the bigger denominator is underneath the x squared. And so that means that the major axis is the x-axis, because 25 is bigger than 9. So a squared is equal to 25, and that means a is 5. A, b, and c are always positive numbers, by the way, so when I solve a squared equals 25, really a equals positive 5 is the only value for a, and then the other vertex will be at negative a, or which is negative 5. So our vertices are at 5, 0, and negative 5, 0. That's part of what they asked us to find. And we also want the foci. Before we get the foci, I'm going to get the ends of the minor. That'll help us sketch, and then once I have the ends of the minor, that'll help me find the foci. So b squared is equal to 9. That means that b is equal to 3, and so the ends of the minor axis are 0, 3, and 0, negative 3. And then to get the foci, we need to find the value of c. And that's where we're going to use this equation, a squared is equal to b squared plus c squared. And that means that c squared is equal to a squared minus b squared. So that's 25 minus 9, which is 16. C squared is 16, which means c is 4. And if c is 4, and this is oriented horizontally, the major axis is the x-axis, then the foci are at 4, 0, and negative 4, 0. We could do a quick sketch here. Those are our two vertices. Here are the ends of the minor. And then these are the foci. just sort of draw this nice continuous curve. And there's our ellipse. Alright, for this next one they give us an equation, just like before, right? They gave us an equation, they wanted us to find some geometric information. We're doing the same thing here. The only difference here is, so they don't ask us to sketch it, but we still need to find vertices, the ends of the minor, and the foci. But the other really important difference is to note that this is not in standard form. So 4x squared plus 16y squared equals 64. It is not in standard form, and the way I can tell is that this is not equal to 1. So we need this to be equal to 1 to be in standard form. And the way we're going to do that is just by dividing both sides by 64, which means we're going to divide all terms by 64. And then reduce these fractions. 4 goes into 64 16 times, so we have x squared over 16 plus y squared over 4 equals 1. Now that's in standard form. We could tell, now that it's in standard form, that this is oriented horizontally. The bigger numbers under the x squared. A squared is 16, which means a is equal to 4. And so the vertices are at 4, 0, and negative 4, 0. B squared is equal to 4, so B is 2. And that means that the ends of the minor are at 0, 2, and 0, negative 2. And then the only thing left to find are the foci. They asked us to find the foci, so we need to get C. So A squared is B squared plus C squared. So 16 is 4 plus C squared. That means that C squared is 12. And if you take the square root on both sides, we get the square root of 12, which is, let's see, 2 times 2 times 3. We can grab that pair of 2s, so 2 times the square root of 3. And that means that the foci are 2 root 3, 0, and negative 2 root 3, 0. Alright. So again, you know, these ellipses have the center at the origin, which means that when we find the values of A, B, and C, that means we've found actual coordinates. We'll talk about adjustments we need to make when we look at other ellipses that are located elsewhere. First, let's do another example, though. We want to, in this case, they're giving us geometric information. We got some information about the minor axis and a point that it passes through, and we're going to find the equation. Right, so we're kind of flipping the kind of given and requested information with this example. The center's at the origin. So I know the basic form, standard form for that equation. I'm just not sure yet which way it's oriented. So here's a big giveaway. It says one end of the minor axis is at 2, 0. So that tells us two things. One, it tells us that the y-axis is the major axis. Because the end of the minor is on the y-axis. The end of the minor is on the x-axis, so the y-axis has to be the major axis. And the end of the minor is at 2, 0. So it tells us that b is equal to 2. And so b squared is 4. These two things together tell us, they give us a good starting point. we have y squared over a squared, right? The y-axis is major, so a squared is under the y squared. And then I know that b squared is 4, so plus x squared over 4 is equal to 1. So this information, just that highlighted piece, gets us almost all the way there. All we need that's left to do is to find the value of a squared. So we need to find a squared. And the only bit of information we have not used yet is that it passes through the point 1 square root of 6. Now, if we know the coordinates of a point that a curve passes through, that means that we can, and it's not the first time we've done this, but that means that we can substitute those values in for x and y. So we're going to substitute x equals 1 y equals square root of 6. So here's our equation. Plugging in our values, root 6 squared over a squared plus 1 squared over 4 equals 1. Now we have an equation that we can solve for a squared. So I'll do some simplifying first. The square root of 6 squared is 6, and then 1 squared is obviously 1. And there's more than one way we could proceed algebraically, but I think it's pretty simple if we just subtract a quarter. So now we have 6 over a squared is equal to 3/4. I'm going to multiply both sides by 4a squared. Do some canceling. And then we get 24 is equal to 3a squared. And now it's all over but the shouting. Dividing by 3, we get a squared equals 8. And so now we can finish writing our equation. Y squared over 8 plus x squared over 4 equals 1. Alright, so what if our ellipse is centered somewhere else? We already basically have the standard form, and we're going to make adjustments to that standard form we already know for the ellipse with the center at the origin, just like we made an adjustment for parabolas with their vertex not at the origin. If the center is the point hk, then I'm just going to replace x with x minus h and y with y minus k. Again, we'll determine which way it's oriented, which will determine which where the bigger number kind of lives, whether it's under the x squared or the y squared term. So this next example just says sketch this curve, x minus 3 squared plus over 25 plus y plus 2 squared over 9 equals 1. So it's in a nice standard form. I could tell that the center is the point 3, negative 2. And I know the value of a, and I know the value of b, right? A squared is 25, so that means a is equal to 5. B squared is equal to 9, and that means that b is equal to 3. Now the bigger number is underneath x, so this is oriented horizontally, so the vertices The vertices will be, now, the vertices, the value 5, a equals 5, doesn't give us the actual coordinates of the vertices, but it tells us how far away from the center each vertex is. And since this is oriented horizontally, I'm going to go 5 to the left and 5 to the right. So I'm actually going to start, I think, with a bit of a sketch here. So the center is at 3, -2. And then I got to go 5 to the right and 5 to the left. There's 5 to the right is the point 8, -2. And 5 to the left, 1, 2, 3, 4, 5, is the point -2, -2. Similarly, I'm going to get the ends of the minor by starting at the center and now going up 3 units and down 3 units. So if I go up 3 units, now I'm here at the point 3, 1. And if I go down 3 units, I'm at the point -5. 3, -5. And now I'm just going to kind of connect with a smooth curve. And they just asked us to sketch it, which if we're just trying to sketch, usually the vertices and the ends of the minor are enough information to get that done. All right, our last example in this section, again, they're giving us an equation, and we want to find the center vertices, and this time also the foci, and then we'll sketch it. So you'll notice this equation is not in standard form. It's all kind of multiplied out. I've got kind of terms collected mostly on one side. So what we're going to need to do is complete the square. Now the process is going to look a little bit different when we need to complete the square on the ellipse. So for starters, I can tell this is an ellipse because both variables are squared. Different coefficients, though. Different coefficients, same sign. And that's how I know that I'm looking at an ellipse. So what I'm going to do is gather my x's with my x squared, my y's with my y squared. I'm going to subtract 8y from both sides. There's no other constant term to worry about. So we've got 2x squared plus 8x plus y squared minus 8y equals 0. Now, when we were completing the square on a circle, our next move was just to divide out by the coefficient on x squared and y squared because we need a 1y squared and a 1x squared. But that doesn't work here anymore because these coefficients are different. If I divide it through by 2, then all of a sudden I've changed my coefficient of y squared from 1 to 1/2, right? So I can't get them both to be 1 simply by dividing. So what I'm going to do is factor out a 2 just from these two terms. So that'll look like this. I take out the 2. Inside now I have x squared plus 4x. I'm going to close the parentheses, but I'm going to leave space. And then I've got y squared minus 8y. I don't have to factor anything out from there because that's already a 1y squared, but I'm going to leave some space, equals 0. Now I'm going to complete the square, and for the x's, I'm completing the square just on this expression here. Right, so the coefficient on x there is 4. I'm going to cut that in half and then square it. So plus 2 squared. Now I've added 2 squared. It looks like I've just added 2 squared, but that 2 squared is inside parentheses being multiplied by 2. So that when I add the same thing to the other side, I'm going to have to bring that over. Plus 2 times 2 squared. So this factor of 2 comes from this factor of 2 that we took out of the parentheses. And then for the y's, we're going to add plus a negative 4 squared, and then plus negative 4 squared. Now, let's see what we got. On the left side, working with the x's, the stuff in the parentheses here, that is a perfect square. It is the square of x plus 2, but I've got to bring down this factor of 2 with me. And for the y's, that's y minus 4 squared. And if we do this arithmetic here, I've got 16 plus 8, so that's 24. Alright, we have completed the square. It's still not in standard form yet. I'm going to give you a few seconds, see if you can identify why it's not in standard form. And to be in standard form, this needs to be a 1, right? So I'm going to divide through by 24. So I've got x plus 2 squared over 12 plus y minus 4 squared over 24 equals 1. There's your standard form. And the center is negative 2, 4. And then we want the vertices and foci, and then we want to sketch it. So we've got a bit more work to do, but we know that this is oriented vertically because the big number is under the y squared. So a squared is equal to 24, which means a is the square root of 24. Now, if I were looking to get exact values, I would just simplify the radical, but we're going to sketch this, and so we're really going to want to get some points that we can plot, and for that reason, I'm going to approximate this. Oops. For about 4.9. A lot of times when I approximate, I might go, more digits, but I'm freehand sketching this, so I don't think I can get more accurate than, say, the tens place. And b squared is equal to 12, which means that b is the square root of 12, and I'll approximate that. And that's about 3.5. Okay, so now, since it's oriented vertically, the vertices, we're going to get by, it's going to have the same x-coordinate as the center, but I'm going to go up and down 4.9 units approximately. So my vertices are negative 2, let's see, about 8.9. Well, let me write it out this way. So that my two vertices are negative 2, comma, and then 4 plus or minus 4.9. We're just adjusting that y coordinate. So that's negative 2, 8.9, and negative 2, negative 0.9. Ends of the minor. Is, let's see, we're going to make adjustments to the x coordinates. So negative 2 plus or minus 3.5, comma 4. So the ends of the minor axis will both be at a y-coordinate of 4. And let's see, we get -2 plus 3.5, that's 1.5, 4, and -5.5, 4. And then they also wanted us to, we were asked to find the foci, so we need the value of c. So a squared is equal to b squared plus c squared, which means that we get 24 is equal to 12 plus c squared. That means that c squared is equal to 12 as well. So c is approximately 3.5. And the foci are, again, they're going to be on the major axis. So I'm going to have the same x-coordinate, -2, and then I'm going to add and subtract 3.5 to the y-coordinate of the center. So 4 plus or minus 3.5. So that's -2, 7.5, and -2.5. Okay, so we found the information that they asked us to find. Now we're going to sketch it. I'm going to scroll up just a little bit, and I'm basically going to use the vertices and the ends of the minor to help me do the sketch. I'm just going to plot these points. So that's up at 9 right there, and down to, there's -1, and so -2, 8.9, that's going to be around there. -2, -0.9 is about there. 1.5, 4 is about there, and -5.5 is about there, and it looks something like this. Not too bad for a freehand sketch of the ellipse.